So we're going to look at the graph, figure out what all's going on here. The first question here, what's it tell us about the race? Well, it tells us a lot of things. You know, it tells us that it looks like it was a back and forth race a decent amount, judging by the number of times the lines are crossing, but we can probably get more specific than that. Like, who won the race?
Blue.
Yeah, A won the race, and we can say that because they reached the 100 meters in the least amount of time. So that means they got there first. Excellent. Did everybody actually finish the race here?
Yes.
Yes, because everybody actually reached 100 meters. Okay. How about a different type of question? Who do you think reached the highest top speed?
A or B, depending,
Well,
depending on the slope.
could it be A?
Yes, absolutely.
Could it be B?
Yes.
Could it be C?
Not.
No. The one thing we can definitely say really easy is that C is not the one that reached the highest top speed. Because if we're looking for that highest top speed, you're looking for who was making the most yards, or the most meters rather, in the least amount of time. So that would mean that their graph would be the steepest. So we're basically kind of looking like, if we were looking at runner B, you know, they were pretty steep through there and pretty steep through there. That was B's top speed. A's top speed looks like it's happening right around here. Looks like it's pretty close. I think maybe A was a little bit steeper there, therefore A might have reached the higher top speed, but it's pretty close. Tough to tell just by eyeballing it. But certainly we can say that C did not, because C never had that steep of a graph. Take a look at B's graph. It looks kind of odd, right?
He fell.
What is happening in here?
He fell.
He definitely.
Yeah, we got different variations of the same idea down here and there.
I think he got a heart attack.
Basically, that runner stopped moving, right?
He would have won it too, probably.
Because throughout this section of the graph, the distance actually traveled is not changing over time. So the person was just holding still. We don't know what happened necessarily, but they were holding still. So we can tell a lot about the graph, but notice a lot of what we were able to tell about it also came back to the idea of the slope of the graph at various points along the way. That's one of the big ideas in this class, is looking at the slopes of the curve as it changes, as you've been seeing with some of those wall map problems, right? You've been seeing on those computer problems that oftentimes you're really comparing the original graph to its slope function and some things like that. All right, so today we're going to be taking a look at writing equations from some information. Take a moment, read through this problem, and think about how would you get your answer. Now, doing these types of problems, one of the best things to do at the start is just focus on this part. Because we can just do this part first, and then we can go and see what happens with the rest after that. All right, so that statement there, f of 2 equals f of negative 3 equals 0. Notice that's giving us a couple points. Specifically, what it's telling us is that if I were looking at a graph of this at x equals 2, the graph would be crossing the x-axis because its y value is 0. Same thing for the negative 3. It'd be crossing the axis there at negative 3 as well. Well, we've seen that before, right? Think factored form to make your life easier. If we were just doing that, how about y equals x and the 2 and the x and the 3? Question though, should it be plus 2 or minus 2?
Minus 2.
And how do we know? Because if I plug this 2 in for x, 2 minus 2 is 0. And we want it to equal 0. And so, yes, that one ends up being 2. Therefore, the 3 should be plus or minus 3. Plus, yes, because I want to be able to plug the negative 3 in for x here and have it be negative 3 plus 3 equals 0. So this works for that part of it. The question, though, is, does it also meet that requirement? F of 1 equals 16. Well, let's actually just test that and see what happens. So, f of 1 equals 1 minus 2, 1 plus 3. So that's going to end up giving us a negative 1 times 4, so that's negative 4. That's not quite it though, is it? Okay, so how can we fix it? Well, can we just, let's see, that gave us negative 4. Can I just add 20 onto the end then?
No.
That would give us this, right?
No.
Would we still get zeros over here?
Yeah. Oh wait, no, you wouldn't.
No. No, that 20 would change that part. They would all equal 20 then, not 0. Okay, so we can't just add the 20 onto the end. We have to still have them be zeros. So it's like then we got to multiply by something. So let's go back to our original equation here. And let's put in a coefficient. I'm just going to call it A for the moment. And so we're going to have some f of x. And we just got to figure out what that A value would be. Well, I can actually plug that A value in down here in this equation. Because if I do that, then that would turn this whole thing into A times the negative 4. I want that to actually equal 16. Notice you now have an equation you can solve. So we divide both sides by negative 4. 16 divided by negative 4 gives us negative 4. All right, so then now we have an equation. So then f of x would equal a negative 4 times the x minus 2 times the x plus 3. All right, now for this problem, it's the same idea. Just in this case, there's 3 different pieces that can all equal 0. That's okay. If I just went through those in the order that they're shown, I'd end up with f of x equals x plus 2. Although, you know, I actually want to keep track of that unknown number because we might have to multiply it by something again. So I'm going to go ahead and put that in there now. Let's do a times x plus 2. And then x minus 1. And then it'd be like x, what, like plus 0 or something like that? We can clean that up. Yeah, let's just clean that up. So if I wanted this to be looking a little bit tidier going forward, I'd probably write it as like a times x, x plus 2, x minus 1. That's at least a little bit tidier to work with. All right, now I can go ahead and go on to this. The f of 2 equals a negative 24. So to use that then, I'm going to do the f of 2 equals, so that's going to be the negative 24 equals a times the x, so that's our 2. And I'm plugging 2 in wherever the x is. And then just figure out what that equals, solve the equation, right? So negative 24 equals a times, that would be 2 times 4 times 1, so that would be 8. So divide both sides by 8, negative 3 equals a. So our final answer then, f of x would equal negative 3x, x plus 2, x minus 1. Yeah, to make sure that you're on the right track, that first one, when we say f plus g, literally all you have to do is take what f equals, which is the x squared minus 6x, and add what g equals, which is 1 over 2x. And that's actually going to be our final answer there. Some people look at it and they start thinking, okay, well, maybe now I have to get rid of the fraction, right? I got to get the x out of there and all that kind of stuff. No. There's no other side to this. It's not like it equals some other equation there. So it's not like I can multiply both sides by 2x because there aren't two sides. So go ahead and just leave it like that. Now, as you're working through these, there might be one thing at this point that you still might have a question about, something that you might get a little mixed up on. The dots. Do you remember what that means and what goes in what? If not, you can always rewrite this. In fact, this is what I often do just to help myself see it more clearly. Those two statements are equivalent. F dot g is the same as f of g of x. So here's your answers for the first column of problems. Do note, we couldn't really simplify anything until the very end, but something to pay close attention to. This sign right here, make sure that's a plus, because we were subtracting the whole original, so minus the negative 6 makes that into a plus 6x. And yes, on this last one, that one can be simplified. So I'd have you simplify it. So when doing the quotients here, yes, we got to do some simplifying on it. So like f over g. Remember, it being over is the same as dividing. So it's like I'm saying I'm taking the x squared minus 6x, and I'm dividing it by 1 over 2x. Well, you remember how to divide by a fraction. We multiply by its reciprocal, which means it's the same as multiplying by, and I should put those parentheses in for clarity, multiplying by 2x. And so when we distribute that in, we get the simplified answer. Same kind of thing happens for g over f, just it's going the other way. So we're doing compositions here, so that means plug the function into the other one. So like that first one, the f dot g. Really what that's meaning is plug this function in here for x, wherever it appears in the other equation. So that means that this one started out before any simplifying as 1 over 2x squared minus 6 times the 1 over 2x. And then we just started simplifying from there. I actually would be okay with either of these two answers. You didn't have to necessarily break it into a single fraction,
Oh, we had to.
but it's good form.
We had to.
And then for the g of f of x, it's the same idea, except I'm taking this whole function and I'm plugging it in for this x here, which is why there's not all that much change to it. We just distribute the 2. And then for the f dot f, it's possible that you didn't get yours looking like that. You might not have expanded it. If you didn't expand it, you would have had x squared minus 6x squared minus 6 x squared minus 6x. But since it is a polynomial, it's a good idea to actually go ahead and give that in standard form. So in other words, multiply it out. That's really because this was squared. If this was instead like a quartic function or something like that, where this was a really big exponent, and multiplying it out would be a real pain, then we could go ahead and just leave it in that kind of a form. All right, but anytime it's a squared, multiply it out, because it tends to be easy enough to do. And finally, the g dot g, plugging g into itself. So that ends up giving us 1 over 2 times 1 over 2x. So you end up looking at this sort of thing. And this is where sometimes people run into trouble with the simplifying. So just seeing the work that we'd end up doing, let's start by dealing with the 2's. This first 2 and this 2 that's in the denominator here, they end up canceling each other out. So we end up actually with 1 over x. Well, that's the same as 1 divided by 1 over x. And if I'm going to divide by a fraction, that means multiply by its reciprocal. Hence why the whole thing just equals x. So what I'd like you to do here is match up each of those 5 graphs with its equation in function form. We don't actually need to know the actual equation for f of x, but we can use what we see visually as clues to tell which one is f of x, and then which one's 2 times f of x, and so on. Match each graph with its function, please. All right, so for the f of x, which graph did you think was f of x? 1, 2, 3, 4, or 5?
4.
Which one?
4.
Well, it's definitely not 4.
Damn it.
I said 5.
You owe him $20.
Oh wait, no, it might be
He
3.
said no to the deal, actually.
All right, so f of x is 5. That's our starting one. So this is what everything else is relative to. So if I take a look at that second one, the difference here is the 2. If I multiply out front by 2, that represents a vertical stretch by a factor of 2. So in other words, I'd expect this point to be twice as high. I'd expect these points to be twice as low. And hence why the answer then would be graph 2.
Yes.
The third one, f of 2x. So you got the number multiplied inside. So that's the horizontal stretch and compression. It's just that we have to remember that the horizontal stretches and compression are counterintuitive. 2 inside actually makes it half as wide. That is a horizontal compression. Therefore, that is graph 3. Same as graph 5, just squeezed in from the sides. Graph 4, or function 4 rather, f of x plus 2. Well, if we're adding directly to the x, that means it's moving it in the x direction. And a plus, it's going to move it left. So it needs to be the same height as graph 5 was, just moved over to the left. That would mean graph 4. And finally then, yes, process of elimination, we could figure out the last one's graph 1, but if not,
Last one's graph 5.
if not, you'll notice that it's, well, it's got the 2 and the x plus 2. It's kind of like graph 2, just move left 2 as a way to see it, because it's twice as tall and shifted left 2 there. Now use that refresher from that last problem to remind yourself how to write each of these in terms of f of x, please. All right, so the first one, we're shifting 3 units up. That means I'm going to take my normal f of x, whatever that is, and I just put a plus 3 hanging on the end. So notice in that case, because it's going up and down, plus 3 is outside of the parentheses, and then the rest will probably go pretty quick, because 2, f of x minus 3 in order to move down. Number 3, we have to put the 3 this time inside with the x, because we're moving in the x direction. The only question is, if we're going to go right, is that going to be plus 3 or minus 3? It is minus 3, yes. If anything trips you up, that's one of the things that might do it, so we pay attention to that one. Number 5, if we're going to reflect across the x-axis, that is flip it upside down, we make the whole thing negative. But for number 6, if we're going to reflect across the y-axis, that means we just make all of the x's negative. And for 7, if we're going to apply a vertical stretch by a factor of 3, that means we just multiply by the 3. And if we want to shrink it vertically by a factor of 3, that would make it like 1/3 f of x. Although honestly, I don't really like the phrasing here, but it is used in the book, so I went ahead and went with it. Shrink vertically, I tend to prefer compress vertically. It makes a little bit more sense. So then here is a little basic graph, a little piecewise function graph. Made it easy to draw, easy to compare as we start coming up with answers. What I'd like you to do is take our drawing of f of x there and draw a graph for each of those 4 functions that is represented. All right, so let's take a look and see how we'd actually go about doing these. Really, as I go and sketch my graphs, I'm going to be focusing basically on the corner points of this piecewise function and kind of moving each of those to be able to see what the overall picture looks like. All right, so for the first one, I got the minus 2 hanging on the end. That tells me that I'm going to be shifting the graph down 2. So I should be taking everything and moving it down 2 like that. So that's what your graph for part A would look like. Just as the exact same thing, move down 2. All right, part B. The minus 2 is on the inside with x, therefore it is moving sideways, specifically to the right. And so our graph should be looking like this time. Maybe a little straighter than that, but there we go. Closer. All right, part C. There's 2 things going on. We got the minus in front and we have the 2. The minus flips it upside down. So like that flat part ends up being down here. But then the 2 makes it twice as far away from the axis. So actually it's going to be going down like this. And you'll notice that our slopes that used to be 1, they're now 2. And so we end up with a graph that's looking like that. And then for the last one, well, the plus 1 is going to move everything up 1, but the 1/3, sometimes that gives us a little bit more trouble. The 1/3 inside is going to be a horizontal stretch. It's actually going to make it 3 times as wide. So like this point right here, instead of it being there when I make it 3 times as wide, that point is actually going to come out to here. But then I also have to move it up 1, so that point ends up here. I'm going to do the same thing with these other points. So let's take this one right here. I'm going to make it 3 times as wide, so instead of over 2, I'm going to have to be over 6. And then again, I also have to move it up 1, and so it ends up over here.
Wait.
Let's now move this point. This point, it's currently over 2. It needs to be over 3 times as far. So that one's going to end up over a total of 6 units. And then I go up 1 again.
Wait, I have a question.
And then one last one. Let's move this point. That's currently 3 units over. So it's going to have to be over 3 times as far. So that means it's going to be over a total of 9. And then again up 1. So then our final result ends up being 3 times as wide and moved up a little bit.